Hello. Today we will start some applications of linear programming. We will see what are called zero-sum games. Reference for this video is section 8.1 of the text. Okay, so let's start with what are zero-sum games. So there are two players, maximizer and a minimizer. Now how does the game proceed? So the maximizer has some m options with him. Okay, 1, 2, 3 till m. You can think of it as he has to choose from m numbers. So these are called his strategies. Now minimizer has n strategies, 1, 2 till n. Now, depending on the choices of the maximizer and minimizer, there is a payoff. And how this payoff is given? It's given by an m cross n payoff matrix. So for example, look at this. So here, max has 5 strategies, 1, 2, 3, 4, 5. Min has 3 strategies, 1, 2, 3. Now this is the payoff matrix. So how do we read this? If max chooses 1 and min chooses 1, the payoff is 10. So what does it mean? So max will receive 10 units of money from min. Okay, so if max chooses 3 and min chooses 2, then min has to pay 3 to max. Okay, so this is how the game is. So max does not know what min is going to play and min does not know what max is going to play. Now based on this, they have to optimize their choices. So we are looking at max as choosing rows of this matrix and min as choosing columns of this matrix. Okay, so the objective of the game is that max wants to maximize the payoff and min wants to minimize the payoff. This is because min is the one paying to max, so min wants to minimize what she gives and max wants to maximize what she gains. Okay, and that is why this game is zero sum. The loss of one player is the exact gain of the other player. There's a payoff of 5 to max is minus 5, means minus 5 to min, and a payoff of minus 3 to max will mean plus 3 to min. But so we will say that the payoff of the game is this choice mij. That's how we have written it, and these numbers denote the money that max gets. Okay, so why are we looking at this these kind of games? It turns out that many situations in economics, AI, game solving, finance, wherever there is a strategic reasoning between parties involved, you can model those situations using zero-sum games. So we will look at it as this matrix and the two players. Okay. So let's see some examples. So how should max and min play in this game? Okay, now suppose, so we start off with this exercise, okay, which we assume that max plays first and after that min plays, knowing what max plays. Okay, so suppose max plays 1. Okay, then what is the best strategy of min? Min has to minimize. So min will play 3. So when max plays 1, best strategy of min is 3 and the payoff will be minus 1. Okay. Now when max plays 2, min has to play the strategy 1 and the payoff will be minus 2. So similarly, I have tabulated for 3, 4 and 5. Max plays 3, min plays 3 and payoff will be 1. When max plays 4, min should play 3 again and the payoff will be minus 2. And when max plays 5, min has to play 2 and the payoff will be -1. Okay, now in this format, suppose Max plays first and then based on that Min plays the best strategy. If this is the format, Max will play the best option among all of these. So if you look at it, if Max plays 1, payoff is -1. If it is 2, it is -2 and so on. So he will look at the max among these numbers, which is 1. Right? So the best strategy for Max is to play 3 in this format. And then Max will receive 1. Because any other strategy that Max plays will get a smaller payoff. Okay. So now let us do the same exercise for the reverse. Let's assume that Min plays first and after that Max plays. So Min chooses this column. So suppose Min plays 1, then Max will choose the maximum among this column and that will be 10. So when Min plays 1, best strategy of Max is 1 and the payoff will be 10. When Min plays 2, the best strategy of Max will be 2 and the payoff will be 4. And when Min plays 3, the best is either 3 or 5 and the payoff will be 1. So if you see that in this case, the Min Max, this is when Min, so Min will choose the min among these things and that is going to be 3. Okay, so knowing that Max is going to play the best strategy against her, Min will choose 3. Okay, so call this quantity min max when Min plays and based on that Max plays. So in this game it turns out that Max Min is 1 and Min Max is also 1. Okay, now let's look at an example of some other game. So what happened? I changed only one value. So this value was 1 here. I changed that value to something else, 7. Okay. Now let's identify Max Min now. So again, when Max plays this, the best is not changing and the min will play 3 and the payoff will be -1. Here also it doesn't change, it will be this. Now here, previously it was 1 here and Min was playing that. But now instead Min will play 2 and the payoff will be 3. So when Max plays 3, Min will play 2 and the payoff will be 3. Here it will not change. It will be this and this respectively. Okay. Now what is the max over all of these? This is going to be 3. Okay. So the best strategy of Max is to play 3. And when Max plays 3, he has to expect the worst. And that will be Min will play this thing. Okay. So Max Min will be 3. Now what about Min Max? When Min plays this is the same, 10. When Min plays this, Max will play this, 4. And when Min plays this, Max will play this, and that is 7. And Min will choose the minimum among these. So here Min Max will be 4. Okay, so here Max Min is not equal to Min Max. Okay. So let's kind of give some remarks about what we did. So when we did the Max Min computation, Max plays first and knowing Max's strategy, Min gives her best response. Okay, so how should Max play? Knowing that Min will play the best response, Max will play a strategy that maximizes the payoff. So that is what happened here. Knowing that Min will play the best response, Max found the strategy that maximized the payoff. Now that is the reverse case for Min Max. When Min plays first, Max gives the best response and Min plays a strategy that minimizes the payoff, knowing that Max will play the best response. Okay, so these are two quantities that are relevant to us when the game is given, Max Min and Min Max. So more formally, here it is. So suppose we are given a game represented by the payoff matrix M. Okay, so let's first give a terminology for the strategies. So for some reason we will call them pure strategies, the choices that Max makes. Max chooses something from 1 till M, they will be called pure or deterministic strategies. And the choices 1 to N of min will be called pure or deterministic strategies. So because later we will see strategies which are randomized. But for the moment, it's a strict choice, either some I and J. Now the max min over pure strategies, we denote it as max min pure, is the max over all I, the min over all j, mij. Okay, that is what is the max over all I. For each I you find the min and you take the max. So for given an I you find the min and you take the max over all these min values. That is this thing. And min max pure is the reverse. Min over all strategies of the minimizer, you take the max over all strategies of the maximizer, mij. So for each strategy of the minimizer you find the max and you take the min over the maxes. Okay, so these are two quantities. So here is the first thing to note, which is you will always see that max min pure will be less than or equal to min max pure. So look at this example. Here max min is 3 and min max was 4 and max min was less than or equal to min max. So before trying to see a proof of this, it will be a good exercise to try to prove it to yourself why max min pure is less than or equal to min max pure. Okay, so now let's see a proof. So here it is. So you look at each I. Suppose I fix an I, a strategy of the maximizer. Okay, and I look at the min over all strategies of the minimizer. Okay, so for each I fix an I and I look at the min. Okay, the claim is that this min is less than or equal to min max. Now we will see this with a better illustration, but for the moment, suppose I give you this fact. For each I, the min over all j, mij, is less than or equal to min max. Then what does it mean? So for every I, you have that this thing is less than or equal to this. So the max of over all the i's will also be less than or equal to this. Right? So if this is true for each I, then this follows easily. Now the main thing is to show this. So here is an illustration of this fact. Okay, so this is what we are going to show. When I fix an I look at the min for this I. That will be, say, some ji. Okay, so this is the min over all j, mij. So what do we want to show? So before looking at it, look at this. So firstly, for an I, my mij1 is the least in the row, right? Which means that this thing is smaller than the first element, the second element, and so on. So mij1 is smaller than or equal to mi1, mi2, and so on. That is what this part is telling. So forget about this for the moment. So this thing just says that my mij1 is smaller than each of them because we have chosen the min. Okay. Now look at mi1. Okay. Now you fix this column for the minimizer and then vary the choice of the maximizer. Now in this column there will be a maximum number. So call it the max over all I mi1. So we have fixed the minimizer's choice. Okay, so mi1 is less than or equal to this thing. Okay, so which means that this original value, this mij1 that we had, that thing will be less than or equal to this value also. Okay, so that is what written here. Similarly, you look at mi2. This will be smaller than the biggest value here. So mi2 will be smaller than max over all I mi2. Okay. Similarly, mi3 will be smaller than max over all I mi3 and so on. The jth thing, mij, will be smaller than max over all I mij. So we get these inequalities. Now we already know that mij1 is smaller than each of them, and which in turn is smaller than the max. So this mij1 is smaller than the max of each column. Hence, mij is smaller than the least among these numbers, and that will be the least among these numbers. mij1 is smaller than the least among these numbers implies mij1 is smaller than min over all j max over all I mij. Okay, and that is what we wanted to show. So for each I, this quantity, the mij, that is the min over this, is less than or equal to min max. Okay, so this completes the proof of this lemma. For a game, max min is less than or equal to min max. Okay, so now, so we have seen that in general max min pure is less than or equal to min max pure, and in some cases a strict equality is also attained. In particular, there was this example where the max min and min max were both 1. So if you notice, this value is the least in this row and the biggest in this column. Okay, so such a point will be called a saddle point. Okay, this is a cell in this payoff matrix which is least in the row and greatest in the column. Okay, so this is what, so an MKL is a saddle point if MKL, so this is the kth row and lth column, it is the min over all j MKJ, and it's also the max over all I MIL. Okay, now here is a statement: a game will have max min to be equal to min max if and only if there is a saddle point. Okay, so I'll leave the proof of this statement as an exercise. You have to first start with, suppose the game has max min equals min max, then you have to show that there is a saddle point, and then you have to take a game where there is a saddle point and then show that for that game max min will be equal to min max. Okay, so I'll leave this statement as an exercise, proof of this as an exercise. So now comes the main definition, which is Nash equilibrium over pure strategies. So when we have a game where max min pure equals min max pure, the game is said to have a Nash equilibrium over pure strategies. So what does it mean? So when this happens, there exist strategies I and j for max and min such that when max plays I, j is the best response of min, and when min plays j, I is the best response of max. So for example, in this case, so let's take the strategy to be 3, 3. When max plays 3, the best response of min is 3, and when min plays 3, the best response of max is also 3. Okay? So these kinds of pairs of strategies are said to be Nash equilibrium strategies. Okay, and the game is said to have a Nash equilibrium in that case. So here is the thing, so the Nash equilibrium strategies are 3 and 3 for max and min. So intuitively, max has no gain by deviating. So if max knows that min is going to play 3, then there is no incentive to deviate, because if max goes to 2, then his payoff reduces. If max goes to 4, it reduces. If max goes to 5, it doesn't change. Similarly, if min knows that max is playing 3, min has no incentive to deviate, because if min deviates from 3, max will get a better payoff. So this is why there is an equilibrium in these strategies and no party wants to deviate. Okay, now so we are done for today's video. So the goal of today's video was to introduce to you what are called zero-sum games and pure strategies in zero-sum games. Okay, and we have defined these two values, max min pure and min max pure, and in general we have seen that max min pure is less than or equal to min max pure. It will be a good exercise to try prove it yourself, why max min pure is less than or equal to min max. And then in some games we have max min pure to be equal to min max pure, and in that case it's called a Nash equilibrium. Okay, so where is linear programming so far at all in all this? Yeah, so far there was no linear programming, but in the next video what we will see is we will see different kinds of strategies. Okay, where max can choose different numbers with different probabilities. Similarly, min can choose different numbers with different probabilities. Okay, and when we allow these kind of strategies, we want to look at max min and min max and then see what happens to these relations. And there we will use a very significant use of linear programming. So the goal of today was to introduce you to the game and these values max min, min max over pure strategies, and the notion of Nash equilibrium over such pure strategies.